Good morning, folks.
Morning.
All right, welcome back, everybody. How you doing today? Okay, I'm seeing many descriptions of being tired. So if you are tired this morning, thank you for showing up for class. I do appreciate it. Okay, I hope you're doing well, and I hope you had a nice weekend. We're going to keep rolling here. We do have lab today, right? We're now a week away from your second lab exam. Okay, and in addition to that, we're going to continue our conversation in chapter 6, so we understand a bit more about bone histology. Okay, so before I resume that conversation with you, do you have any questions right now? Okay, gang, hang in there. We are at that tipping point in the semester. You are actually closer to the end of your semester than the beginning of it at this moment. So hopefully that makes you feel good. We're going to have to wrestle to fight that sensation of tiredness the remainder of the semester, because, that's how it is when you're going into something really in depth. So hang in there, give yourself moments of rest, and then try your very best to get back on the saddle for studying. Okay, let's continue chapter 6. All right. I'm going to share my screen with you. Okay, so you recall from last time, we were talking about the various types of cells that we might find at different stages of our lives in terms of bone development, okay, bone composition. And I was highlighting several of the bone cells that you see in figure 6.2, figure 6.2 on page 181. And so I won't rehash those, but there were basically 4 cells we had placed into your notes. Those would be osteoprogenitor cells, also called osteogenic cells, osteoblasts, osteocytes, and osteoclasts. Okay, this is the last piece of note that was put in your notes from last time, where we were trying to be sure that you understand the difference between bone deposition and bone resorption. Okay, so the osteoblasts, those kinds of cells that we call osteoblasts, are responsible for manufacturing and releasing the materials that become the extracellular matrix of our bones. Okay, if we have the ability to build extracellular matrix, then we also at times in our lives need the ability to break that extracellular matrix down, right? I mean, if our calcium levels are too low in our bloodstream, then we need to pull calcium out of the extracellular matrix of our bone, and we do that by a process known as resorption. Resorption is the responsibility of cells called the osteoclasts, which again you see in figure 6.2. Okay, so there is this constant tug of war in our body. It's kind of like you have a seesaw with osteoblasts on one side of the seesaw and osteoclasts on the other side of the seesaw. And based on environmental stresses that you're placing your body on, or you are not placing your body on, these cells will be active. For example, if before the coronavirus pandemic hit, you were regularly exercising at the gym and lifting weights, then that would mean that your bones needed to have a higher density to them to be stronger to do the weightlifting activities you were enjoying in the gym. So the osteoblasts inside your bone tissue would have been very active, maintaining a dense extracellular matrix. Once coronavirus hit and some of the gyms were locked down, you couldn't go exercise as much as you want. So you maybe had stopped exercising for a while. Well, at that point, your bones say, well, okay, nobody's stressing me out by lifting weights anymore, so I don't need to maintain a very dense extracellular matrix. So in that case, the osteoclasts would have cranked up their activity and actually nibbled away some of the extracellular matrix inside your bones and reduced your bone density, okay? So depending on your lifestyle choices, whether you exercise or don't exercise, depending on your nutrition, what kind of foods you eat or don't eat, depending on your personal health status in terms of any infections you're fighting or not fighting, there's going to be a tug of war on the activity of the osteoblasts and osteoclasts, okay? There's a constant tug of war between osteoblasts and osteoclasts to maintain the proper physical characteristics of the extracellular matrix to support bone density. Okay. Now, understanding what these osteoblasts and osteoclasts really are doing is difficult to envision. It's difficult to imagine. I mean, we can read these things in the textbook and we say, okay, yes, I kind of get what you're telling me, but it's hard to visualize it. It's hard to imagine these things if you don't have a way of thinking about them. So folks, I'm going to start today by really showing you a little video, which, if I'm completely honest, is not the best video in the world, but it is the best video I've ever found describing this topic. Okay, it's not the best video, but it's the best video that I've been able to discover that at least gives you some way to visualize these processes. Okay, so I placed the URL for these videos, for this video, at the top of your notes today, and I'm going to show it to you at this time. It's about a 3 or 4 minute video. Okay, so let's watch this video, which is available to you on YouTube, and then we'll continue our conversation after that. All right. Okay, so the title of this video is Bone Remodeling and Modeling. Okay, and here we go, folks. Enjoy.
The skeleton changes across the human lifespan. This is characterized predominantly by bone formation and growth throughout childhood, followed by a gradual loss of bone density that begins in early adulthood that can accelerate significantly in older adults. The density of bone is modulated by a group of cells including osteoclasts, which are multinucleated cells that resorb bone, and osteoblasts, which refill the resorption cavities created by osteoclasts. Osteoclasts anchor themselves to the surface of bone. This creates a microenvironment underneath the cell, which is referred to as the sealed zone. Within this zone, the osteoclasts create an acidic environment that dissolves the bone's mineral content. Once the mineral content of the bone has been dissolved, enzymes released from osteoclasts remove the remaining collagenous bone matrix to complete the process of resorption. Following resorption, osteoblasts move into the resorption space and start to produce and deposit organic matrix called osteoid. Osteoid, a substance made predominantly of collagen, forms a scaffold in which minerals including calcium and phosphate begin to crystallize. Some active osteoblasts become trapped within the matrix they secrete and thereby become osteocytes. Other osteoblasts will undergo apoptosis or will revert back to lining cells which cover the surface of bone. This cycle of bone resorption and formation is referred to as remodeling. There is also a process where bone formation by osteoblasts occur without prior bone resorption by osteoclasts. This results in an increase in bone mass and is referred to as bone modeling. Bone modeling promotes the growth of bones and is important for maintaining bone strength. Remodeling also plays an important role during bone growth by optimizing the growing structure. After the age of 30, most people experience a gradual loss in bone mass due to a relative decrease in the activity of osteoblasts compared with osteoclasts. However, there are many factors that impact the process of bone remodeling and influence the degree of bone loss we experience as we age. For example, medications such as glucocorticoids, which can promote osteoclast activity and also reduce bone formation. Proper nutrition and physical activity can help strengthen bone. It is also believed that osteocytes form a complex network in bone that can sense any increased workload on the bone and respond by triggering the differentiation and activity of osteoblasts to increase bone density. Conversely, when bone experiences reduced loading conditions, such as during long-term bed rest, resorption and remodeling increase to eliminate underloaded bone. Loss of bone mass reduces its strength and increases the risk of fracture. This highlights the importance of staying active, maintaining good nutrition throughout life, and being aware of personal risk factors associated with low bone density.
Okay, folks. So, this video, it's okay. It's not fantastic. The truth of the matter is that when we think about our bones, how the bones form in the womb and how our bones maintain their shape and structure throughout our lives is largely an invisible process that we really can't see with our naked eye, can we? We don't think about it. We don't see it on a traditional everyday scale time frame. So there's still a lot of mystery of exactly what's actually happening in the bone. It's a very active area of research for things that we're still trying to understand. But I hope the video gave you at least a little bit of way to start thinking about what these cells are and what they're doing inside your bones. Okay. Do you have any questions from having watched the video one time? Okay. Well, let me just make two more comments about this topic, and then we're going to move forward to the next conversation in the chapter. Okay. I think I mentioned last time, I may have mentioned last time, a disease called acromegaly. So we appreciate that. I'll just put this as bone disorders here. And this will not be an exhaustive list, but okay. Acromegaly is a bone disorder which caused by an excessive deposition of extracellular matrix. Okay. This bone disorder is highlighted by overly thickened bones, which have excessive extracellular matrix. This disorder is thought to be the result of excessive osteoblast activity. Okay, and if I didn't show you a photograph last time, I'll bring one up at this time to let you see this. Okay, so we had this image before, right, where you can see the difference between a normal hand and a person with an acromegaly hand. Notice how the digits, the fingers themselves, are just thicker than you would typically expect them to be. Let's see here. Okay. Let's see here. You also see, I'm trying to look for a time profile here. I mean, you can look at someone like this gentleman here, okay? You can see he has a very prominent prominent facial features, very thick jaw, very thick forehead, bony features up here. Okay, so that would be characteristics of acromegaly associated with excessive osteoblast activity, excessive bone deposition. Okay, at the same time, you are probably more aware of a bone disorder called osteoporosis. Okay, so this is sort of a brittle bone disorder, which is caused by excessive bone resorption or lessening of the extracellular matrix. I'll do this excessive thinning of the extracellular matrix. And this is thought, osteoporosis is thought to be caused from excessive osteoclast activity. Of course, the $9 million question in any of these diseases is, well, why are the osteoblasts overactive in the case of acromegaly? Or why are the osteoclasts overactive in the case of osteoporosis? So an image for osteoporosis would be some images like this. Let me bring this one up here. Okay. And you can see normal bone on the left side, and on the right side, you can see osteoporotic bone, which is a bit more open. It's a bit more airy. There is simply less extracellular matrix present in the osteoporotic bone. So osteoporotic bone is less dense, and by less dense, we mean more brittle. Okay. All right. So let me just ask a question in the chat window. Do you know anyone with either acromegaly or osteoporosis? I would say it's probably more common that you might know someone with osteoporosis. I mean, if you know a senior citizen, and it is more common in women than in men, but if you know a senior citizen, then you probably know someone with osteoporosis, even if they don't talk about it, or even if they haven't been medically diagnosed with it. It's very likely that you do know someone with osteoporosis. Years ago, my aunt, who's now passed away, she was walking along the sidewalk and she just stepped off a curb and literally her hip fractured. I mean, she didn't do anything unusual. She was just walking. She was just stepping down off a curb and her hip fractured. That's the kind of thing that happens when you have overly brittle bones. Okay. All right, folks, do you have any thoughts or questions about deposition or resorption? Okay, all right, let's continue here. Next, we're going to go into a quick description of compact and spongy bones. I'm going to turn your attention, please, if you have your books open, to figure 6.3. Figure 6.3. Figure 6.3. All right, so first off, when we're talking about the compact and spongy bone, we need to orient ourselves. So if you have figure 6.3 available, I want you to really take a look at that image, take a look at panel A, which is sort of the big picture in the middle of the page there, and take a look at the bottom of that middle picture. You're going to see two brackets. One bracket's on the left side called spongy bone. The other bracket's on the more center and right side called the compact bone. All right, so let me ask a question in the chat window. Which type of bone tissue, compact or spongy, is more internal in the bone? Which is further away from the surface of the bone? Okay. All right. So thank you for those that are contributing a response there. And just folks, take a look at the answers that you're seeing in the chat window. Let me repeat my question. Which type of bone tissue, compact or spongy, is more internal in the bone, which is to say further from the surface of the bone? And you can see that there's some disagreement in the chat window, right? There's some disagreement. So before I just give you the answer, let me point something out here. Okay, let me point something out. If you have figure 6.3, okay, let me ask this question. Okay, the question is on figure 6.3, is the periosteum closer to the compact bone or the spongy bone? Is the periosteum closer to the compact bone or the spongy bone? You can see, right, folks, that the periosteum is now, as you look at it, it is closer to the compact bone, right? So we know that the periosteum is on the surface of the bone. The periosteum is on the surface of the bone, and the periosteum is closer to the compact bone, which tells you by reason and logic that the compact bone is on the surface and the spongy bone, coming back to my previous question, is more internal, it's more deep. Okay, so spongy bone is deep inside the bone, compact bone is more towards the surface of the bone. That's what I'm trying to get you to appreciate at this time. Okay. So is this making sense, what I'm trying to get you to see, folks? Any questions? All right, so right now we're going to start talking about compact bone, which is the type of bone tissue we find more at the surface of the bone structure itself. All right, so compact bone is found at the surface of the bone. Okay. This type of bone tissue is immediately underneath the periosteum. And we covered the periosteum last time when we were talking about the structure of a typical long bone. Okay, so if you think, you know, we're approaching Halloween weekend, right? We're approaching Halloween weekend. If you think about, you know, walking down the street and seeing Halloween decorations out, and inevitably someone always has a very classical skeleton out, right? It's part of our Halloween tradition. You know, as you look at the surface of the bones of that Halloween skeleton, if that is a faithful replica of a true skeleton, then you're looking at the surface of the compact bone. Okay, when you look at the bones of the skeleton, when you look at the surface, you're looking at compact bone. Okay, compact bone, if we think about compact bone versus spongy bone, compact bone is the stronger type of bone tissue. Okay, compact bone is stronger than spongy bone. There are many reasons for that, not the least of which is due to the organizational structure of the compact bone. Okay, so let's start talking about that. You know, when you take a beginning For many of you, this is a beginning science course in terms of your career trajectory. When you take a beginning course, right, there's certain pieces of foundational knowledge we want you to walk away from the course with that we hope that stick with you. Examples of foundational knowledge would be, what are the 4 categories of organic macromolecule, right? Carbohydrate, lipid, protein, nucleic acid. Here's another foundational piece of knowledge. What are the 4 tissue types, right? Epithelial, connective, muscle, and nervous tissue, right? Foundational knowledge. So when we talk about compact bone, a small piece of foundational knowledge would be the realization that compact bone, as you look at the picture in figure 6.3, is made of these cylindrical building blocks that are repeating each other. And these cylindrical building blocks are called osteons. Okay, take a look at figure 6.3 and be sure that you can identify an osteon. Compact bone is made of repeating units called osteons. Okay. Osteons are also known as Haversian systems. You might see them described in other textbooks, other pieces of education and training that you come across. But I'm going to stick with the nice simple term osteon. Okay, let's take a look at the structure of the osteon that you see in figure 6.3. And many of you maybe have been studying some of this as you've been identifying the characteristics of bone tissue for your lab, right? And in the histology packet, each osteon is made of concentric bands of material that are called lamellae. Okay, the lamellae are really rings of crystallized minerals is what they are. Each osteon is made of concentric lamellae, which are mineralized rings around a central or open canal. And it's important that you appreciate that canal, right? That canal, you can see blood vessels inside it. In reality, in some areas of your bone, you might also see nerve fibers that go down that canal as well, okay? The central or Haversian canal is used by blood vessels and nerve endings to penetrate deep into the interior of the bone tissue and provide the necessary oxygen and nutrients in the case of the bloodstream, and in terms of the nerve endings, provide sensory capability to deep inside the fabric of the bone for the nervous system. Penetrate deep into the interior of the bone. Okay. The osteons, which again are cylindrical tube-like structures, they run parallel to each other. Okay, so they're next to each other. If one hand is an osteon, then I have another one right next to it. They run parallel to each other along the axis of long bones. Okay. If you look very carefully at figure 6.3 and you look at the osteon and you look at the picture, there's a little arrow that's highlighting a blown up diagram, Okay, so take a look at the osteocyte there. Okay, so let me make a couple notes about this. Okay, so in between the lamellae, in between the concentric rings of minerals, there are these spaces called lacuna, singular, or lacunae for plural. Oops. Wrong location. In between the lamellae are spaces called lacunae. Let me highlight some of these words, right? Because these words are really good vocab words for exams. Okay. Lacunae, and these lacunae, they're actually crevices or pockets inside the bone tissue itself that will be deep enough to hold a cell, like an osteocyte. So, for example, if you could imagine walking along the Gettysburg battlefield immediately after the Gettysburg Battle of the Civil War. Let's say you're walking slowly along the ground and you find an area of earth that has been carved out by the impact of a cannonball so that there's a divot, a depression, a cavity in the soil where a cannonball hit the surface of the ground and blew a hunk of soil out of that location. So there's a depression there, there's a cavity, there's a hole. That's what a lacuna is. It's a hole, it's a cavity, it's a depression, literally in the anatomy of the bone tissue itself that your body will fill up with a bone cell. So a lacuna is a open space or cavity, okay, where you will find osteocytes, which you recall from our conversation are bone maintaining cells. You could, depending on the stage of development, you might find an osteoblast inside a lacuna. It doesn't always have to be an osteocyte. So in between the lamellae are spaces called lacunae, which contain bone cells, osteocytes. All right. In between the lamellae, branching off the lacunae. So definitely take a look at figure 6.3, the upper right picture, the blown up magnified image there. You see an osteocyte, you see bone lacuna, okay? There's something else. There are these little branches that come off the lacuna, which are called canaliculi. You see the canaliculi. It's a very peculiar word, okay? So branching off the lacunae are small channels called canaliculi. That's another good vocab word here. So let's underline it. The purpose of canaliculi are to provide little channels, little burrows through the soil, through the matrix of the bone tissue that allows osteocytes to extend little cytoplasmic arms out and to form a cytoplasmic network from one cell to another, okay? In addition to that, these channels allow for nutrients from the blood supply to ultimately reach the cells of the bone so that they can get their nutrients and oxygen supply to actually live, okay? Branching off the lacuna are small channels called canaliculi, which allow extensions from the osteocytes to touch other osteocytes. Additionally, the canaliculi are used to deliver oxygen and nutrients into bone cells. Okay. All right. Folks, do you have any questions about some of these new vocab words that are being described about compact bone in figure 6.3? hopefully some of these terms are not completely foreign to you, as some of your laboratory homework in Wiley Plus, brings these topics up. Okay, so we have compact bone tissue. That's on the surface of a traditional bone. Okay, this is the tissue that's immediately underneath the periosteum. Next, let's talk a little bit about the spongy bone. Okay, the spongy bone is also shown to you on figure 6.3, but it's going to be the bone tissue that's more internal, more deep inside the depth of the bone. It's deeper to the compact bone. Okay, and as a bracket, you see it along the left side of panel A there, figure 6.3. Okay. All right. So number one, spongy bone is located in the interior of the bone. Deep to the compact bone. Okay, deep to the compact bone. All right. Next, number two, we said that compact bone is stronger than the spongy bone. And one of the reasons for that is because of those concentric tubular structures called osteons that are running parallel to each other. Notice as you look at the fabric of the spongy bone, either in picture A or you look at pictures B and C, what you notice is the absence of osteons. So spongy bone does not contain osteons. And that goes a long way to explain why spongy bones are weaker. Spongy bone tissue is weaker than compact bone. Notice the absence of osteons in spongy bone, which helps explain why spongy bone is weaker than compact bone. Okay. Spongy bone is also known by two other synonymous terms. Spongy bone is also known as trabecular bone. Or in some cases, you might find it called cancellous bone. Okay, that's a peculiar word with this spelling, C-A-N-C-E-L-L-O-U-S. Spongy bone is also known as trabecular bone or cancellous bone. Okay. All right. Now, that word, I'm going to focus on that word trabecular a little bit. Okay. If you take a careful look at the spongy bone of, well, okay, let's see here. If you look at panel A along the left side, you see the quote unquote along the left side terms, you see the phrase spongy bone trabeculae. Spongy bone trabeculae. In the bottom left corner of figure 6.3, panel B as in boy, you see the enlarged aspect of the spongy bone trabeculae. So just take a look at the trabeculae. The term trabeculae literally means little beam. And that's a characteristic, that's a physical observational characteristic of spongy bone. That spongy bone is made of these little beams, these little girders, if you will. Not girdle, that's odd, right? Girders called trabeculae that form these branch-like network of bone tissue. Okay. Spongy bone is characterized by the presence of trabeculae, which means little beams. So answering Fei Lin's question in the chat window, yes, Fei Lin, we are still on figure 6.3. We are still on figure 6.3. Okay. All right. Now, if you were to go with a tiny little scalpel and dissect the trabeculae themselves, the little beams, what would we find? Well, we would find things that you're already familiar with, okay? Within each trabeculae, you will find lacuna, just like we did in the compact bone. You will find canaliculi, just like we did in the compact bone. You will find osteocytes, osteoclasts, osteoblasts at various stages of bone development, just like you will in the compact bone. Really, the primary physical difference between the compact bone and the spongy bone is how the material is organized. Compact bone, you're going to find osteons. Spongy bone, you will not find osteons. Okay. All right. Now, there's an important idea here. You know, we talked about the structure of a long bone last time. We made some fairly extensive notes about that. And we mentioned the medullary cavity, right? The medullary cavity. So, folks, I want you to appreciate that as you look at the spongy bone along the left side of panel A of figure 6.3, what you'll notice is in between the trabeculae is a lot of open space. It's hollow, right? It's empty, it's open, it's kind of airy in a sense, if you will. And it's not literally air because there's not air there, but it's an open space. You don't find other materials present per se. But what I want you to appreciate is that the open space in between the trabeculae can be used to store both yellow and or red marrow, depending on the type of bone that we're talking about, okay? So, you know, Mother Nature likes to be very efficient in how she uses space in your body. And this is one way that Mother Nature is efficient in that regard. The open space between the little beams is sometimes used to store marrow, both red and yellow marrow. Remember, you're not going to store red and yellow marrow at the same physical location. You're going to store either red or yellow, one or the other in that location. All right. Okay, folks. Gang, do you have any questions about compact bone or spongy bone? Okay, let's keep rolling here. Let's see here. All right. So I'm going to give you just a couple quick notes about bone formation. You know, as a topic, I don't think bone formation is the most important thing that you would get out of this chapter, but I should at least define a couple things for you. So let's talk a little bit about bone formation. And to do that, you might want to turn to figures 6.5 and figure 6.6, right? They're on opposing pages in my book, page 186, 187, figure 6.5, figure 6.6. Okay, please understand that the information in figure 6.5 and figure 6.6 are models. And what I mean by models is they are the scientific community's current best understanding of how these processes work and unfold. It doesn't mean we have all the details right. Okay, it's kind of like a weather model, right? A weather model helps to explain and make a prediction about weather patterns, but they're not always right. These are models of bone formation. We know some things about bone formation, but there's some things we don't know. Okay, so take the information here with a little grain of salt, okay, because Let's be honest, science is not perfect. We don't know everything. Okay. All right, let me mention a couple talking points here. Okay, so bone formation from a formal perspective is also known as ossification or osteogenesis. Okay, so if you hear the words ossification and or osteogenesis, that's a way of being fancy and saying, well, this is bone formation. Okay. Number two, bone formation typically happens in 4 different scenarios during your developmental pathway. Okay. Those 4 different scenarios are as follows. You're going to have bone formation during embryonic and fetal development before you are ever born. Okay. You're also going to have bone formation during the growth of your skeleton in periods of your life that we traditionally call your infancy, your childhood, and your adolescence. Okay. So infancy, childhood, and adolescence are stages of your development where you're going to have additional bone formation. Third one, you're going to have bone formation during the remodeling of your bone. Okay, the remodeling of your bone. So, you know, if the osteoblasts need to deposit some extracellular matrix down to build more dense, stronger bones to handle your weightlifting activities in the gym, that's going to be bone formation processes as well. Okay. And the fourth scenario that you're going to get bone formation, you can probably predict, is going to be during the repair of a bone fracture. Okay. All right. So there are 2 primary methods that science believes occurs to build bone in your body, and they are the topics of figure 6.5 and figure 6.6. Okay. They are the so-called intramembranous ossification and endochondral ossification. Okay, we'll list these out for you. Intramembranous ossification is a form of bone formation in which the bones develop directly out of that layer of connective tissue stem cells that I mentioned last time in your notes, and which is in chapter 4, called the mesenchyme. Okay, intramembranous ossification. In this process, bones are formed directly in the mesenchymal layer of cells. Okay, so remember, the mesenchyme is a primitive embryonic type of connective tissue stem cell. Okay, and I'm not going to go into any detail about the process. The process is something that we still largely are kind of that we just don't understand that well. I would encourage you to read the major bullet points of the figures as you do your private study. Read through it once or twice, make sure that what the book is telling you makes sense, but don't worry too much about it. Okay, in terms of your skeleton which bones of your skeleton form through this process called intramembranous ossification. Well, let me tell you a few of this. Okay, so bones of the skull, most of your facial bones, your mandible. Oddly enough, the medial part of the clavicle is formed through intramembranous ossification as well. So bones of the skull, most facial bones, the mandible, and the medial portion of your clavicle are formed by intramembranous ossification. Okay. You're also aware, because of your time studying the skeleton, you're also aware of the fontanelles, right? The soft spots in the infant skull. Okay. After a child is born, those soft spots will gradually ossify and turn into actual bone tissue. Well, the fontanelles will harden through the process of intramembranous ossification. Hardening of the infant fontanelles also uses intramembranous ossification. Okay, so everything else in your skeleton, okay, all the other bones of your skeleton, is made by the other bone formation process called endochondral ossification. Endochondral ossification, bones that form through endochondral ossification form by first developing a mold of cartilage. This is why this is called the hyaline cartilage model. Endochondral ossification is a hyaline cartilage modeling process. Okay, bones form within and replace hyaline cartilage. Okay. By far, most of the bones of your skeleton develop in this manner. Okay. Okay. So it's kind of difficult to visualize what this is. And so let me use an analogy with you here. Okay, so let me ask a question in the chat window. Okay, here we go. Have you ever made, or have you watched anybody ever make Christmas cookies where the cookies look like trees or reindeers or Santa Clauses, a physical object of one kind or another? Maybe Christmas balls you hang on the tree. You know what I'm talking about, right? So most traditionally, how are those Christmas cookies made? Well, we won't go into the composition of the batter, but what I'm trying to get at is, have you seen people take a Christmas cookie tin or pan, kind of a metal mold, which has a depression in the shape of a tree, a depression in the shape of Santa Claus's face, and you pour the batter into the metal depression of the cookie sheet itself, and what happens, you cook the batter and you let it cool and you form a cookie, right? So what I'm saying is that endochondral ossification is similar, because what you do is you build the cookie sheet first. You build the cookie sheet first. You build the tin of metal first, and then you replace it with bone. Okay, so endochondral ossification is kind of like making Christmas cookies. Okay. So what will happen is, first, the cookie sheet, the tin made of metal, is actually constructed from hyaline cartilage, right? So you actually make the cookie sheet itself, and you make it from a mold of cartilage, right? You develop a mold to create bones by forming a framework out of cartilage. Okay. Next, that framework of cartilage is replaced with bone tissue, so-called osseous tissue. Once the hyaline cartilage framework is manufactured, it is subsequently replaced with legitimate bone tissue, osseous tissue. And that's, that's what I would want you to take away basically from your time studying this, okay? If you look at figure 6.6, let me simply read the major bullet points of figure 6.6, and I hope you have that up on your screen or open in your textbook at this time. Figure 6.6, stage 1 says development of the cartilage model. That's what I'm talking about here with my analogy, where before we create the Christmas cookies, we got to make the Christmas cookie sheet. We've got to make the Christmas cookie sheet. That's made of hyaline cartilage. It's number 1, development of the cartilage model. It says here, mesenchymal cells develop into chondroblasts. Chondroblasts are cartilage building cells which form the cartilage model. Basically, your body, through mysteries of Mother Nature that we still do not fully understand, the genetic programming of your primitive cells has the ability to actually form all your bones in their shapes, which, is an amazing thing, and we really don't understand how that actually happens. I mean, if I'm being honest, we don't understand it, okay? But somehow it does happen, okay? So you build the cookie sheet here. Number 2, growth of the cartilage model. Growth occurs by cell division of the chondrocyte. So we start with a little tiny cookie sheet, and we kind of build it and make it larger, continuing with the development of the cartilage. Number 3, development of the primary ossification center. In this region of the diaphysis, which you remember from last class, bone tissue has replaced most of the cartilage. So it's in that diaphysis region that you start replacing the cartilage with actual osseous tissue. Number 4, development of the medullary cavity. Bone breakdown by osteoclasts forms the hollow space where we can put bone marrow into it. Yellow marrow typically in the diaphysis. Number 5, development of the secondary ossification centers. These occur in the epiphyses of the bone, so the proximal and distal ends of the bone. Number 6, formation of the articular cartilage and the epiphyseal growth plates, right? Both structures consist of hyaline cartilage. The articular cartilage is made of hyaline cartilage that lacks a perichondrium, and then there is also hyaline cartilage in the epiphyseal plate, which does contain perichondria. Okay. All right, folks. So, this is a working explanation of what we think is occurring, but there's still a lot of mystery in how your bones really form. All right. I mean, again, it's invisible, and it's a really hard topic to actually study in the lab. I mean, how do you study processes that are largely invisible? It is a technically challenging topic, which is why our knowledge and understanding of it is limited. Okay. All right, folks. So endochondral ossification. Most of your bones of your skeleton are made this way. You start out by creating a bone that's literally made of cartilage first, and then you gradually replace that cartilage with legitimate bone tissue. That's how most of the bones of your skeleton are made. Folks, do you have questions right now? Okay, let's see here. I'm going to jump to the next topic, which is factors affecting bone growth and remodeling. So there's no pictures here for this topic, but if you're following along in your textbook, in my textbook, this major heading of your text starts on page 191, page 191, factors affecting bone growth and bone remodeling. Okay. All right, gang. So let's see what we can tell you here. All right. Well, okay. Let's see. It probably makes sense to put this on a whole new page here. Okay, here we go. Number one, minerals. That shouldn't be a surprise to you, right? You already know that the extracellular matrix is largely made of crystallized mineral salts. Okay. So large amounts, very large amounts of calcium and phosphorus minerals are needed for growth of your skeleton. And of course, you're going to get those minerals from your diet, right? You're going to consume foods that contain calcium and phosphorus. In addition to calcium and phosphorus, I mean, these are the major players. There are also some other minerals that are also important for your overall health and functioning of the skeleton as an organ made of multiple tissues. You also need small amounts of magnesium, fluoride, same fluoride that's in your toothpaste, and manganese. Okay, small amounts of magnesium, fluoride, and manganese are needed for bone remodeling. Okay, these substances that we're talking about, magnesium, fluoride, and manganese, right? These are all elements on the periodic table, right? These are all elements on the periodic table. These substances we're putting into your notes, they act as cofactors for enzymes. Okay. Now, we haven't gotten into a lot of detail about the biochemistry of enzymes yet. You'll get a little bit more about that in A&P 2, and you'll get even more of that in microbiology someday when you take microbiology. But enzymes, as you know, are traditionally made of proteins. However, that's not the whole story. From a biochemistry perspective, an enzyme is made of a protein portion and a non-protein portion. So it's kind of like where you have an airplane, you have the pilot and you have a co-pilot, all right? So the cofactor is the co-pilot. The cofactor is the co-pilot, which is part of the structure of the enzyme. Long story short, these substances, magnesium, fluoride, and manganese, help the protein portion of the enzyme fold into the proper three-dimensional shape to have correct biological activity, to catalyze a chemical reaction needed to support the bone remodeling chemistry. Okay. In short, these substances help the enzymes fold into their proper three-dimensional shape so they can perform correct chemistry in the bone. Okay. And you appreciate everything we're talking about here, whether we're talking about a tissue, an organ, or a cell, everything ultimately focuses down onto the biochemical level, right? We're just not talking at that level of abstraction most of the time in this course. Someday you might need to take, for better or worse, you might need to take a full biochemistry class. Okay, so mineral is very important for the growth and remodeling of bone. Vitamins, also critically important, okay? Vitamin A is a vitamin that's important for stimulating osteoblast activity. If you were deficient, well, let me ask you this question in the chat window here. Since vitamin A is important for osteoblast activity, if you were deficient in vitamin A, would you anticipate a problem with having very dense bones or having very brittle bones? What do you think, folks? If you were deficient in vitamin A, do you think you would end up having very dense bones or very brittle bones? Okay, so thank you, Christina and Christian, Sierra, for contributing, right? It's important to think about these things, right? All right, good job, folks. I mean, there is some disagreement there in the chat window, but here's the deal, right? Osteoblasts are important for bone deposition. Bone deposition increases the density of bone. So if you lack vitamin A, the osteoblasts are not going to do their job. You're not going to deposit, which means your bones are going to be more brittle. The answer is you would anticipate a problem with having brittle bones, not dense bones. Okay. All right. So vitamin A stimulates the activity of osteoblasts. Vitamin C is important for collagen synthesis, right? So remember, collagen is the steel rebar of our extracellular matrix. Without vitamin C, collagen synthesis is slowed down and impaired. Vitamin D is, as you know, critical for the absorption of calcium from food. Okay. One thing that I did not make a big deal of, but let me see here. If you're back on figure 6.6, okay, figure 6.6, calcium itself as a substance is needed to actually build and form your bones. If you look at figure 6.6, take a look at stage 2. Take a look at stage 2 and look at the drawing there. Do you notice where it says calcified extracellular matrix? Calcium is needed during the bone formation process. Also, stage 4, take a look at stage 4, calcified extracellular matrix. So without going into a lot of chemical detail at this point, the point is, without vitamin D, we don't have calcium. Without calcium, we can't really build and maintain the physical structure of the bones either. All right. Next, vitamins K and B12 are needed for the synthesis of other proteins that are important in bone physiology. I mean, it would be a little bit pointless to give you a laundry list of these things because at some point you just can't memorize all this stuff. So we just have to have tables and databases where we look things up. Okay, vitamins K and B12 are needed for the synthesis of additional proteins important for bone health. Okay. Number 3, so minerals are important, vitamins are important. Let's talk a little bit about hormones. Okay, we haven't talked much about hormones in this course. You'll get more of that in A&P 2. But of course, you're aware of hormones. Okay, so you're all aware of the hormone insulin. Okay, I've used insulin as an example in earlier conversations with you. In addition to insulin, there are hormones that are similar to insulin, and their names are insulin-like growth factors. Insulin-like growth factors. Okay. These are proteins. Okay, they're hormones, but as hormone biochemically, they are proteins. So remember, some proteins can function as hormones. So insulin-like growth factors are hormones made of protein constructed inside liver and bone cells. Okay, constructed inside liver and bone cells. And these insulin-like growth factors promote mitosis, which is to say cell division. Put this down as a different bullet point. These hormones stimulate cell division at the epiphyseal plate and in the periosteum during child growth. Okay. Question in the chat window. From a logical perspective, if your physical bones get larger, does it make sense that the membrane around the bone, the periosteum, must also enlarge to accommodate the growing bone? Okay, we can't grow our bones if the membrane around the bone doesn't also get larger. So there's going to be cell division of the cells that make up the periosteum membrane as well. Okay. So these cell divisions are stimulated by these insulin-like growth factors, which are a type of hormone. Okay. Okay, some additional things. Thyroid hormones. Which you may know, there's different thyroid hormones. There's T3 and T4 here that's most relevant for bone physiology. These hormones made by the thyroid promote the growth of bones by stimulating osteoblast activity. Okay. We also have insulin itself. I know I'm out of time, folks. Just bear with me here a second. Okay, so we have the insulin-like growth factors of note letter A there, 3A. We also have insulin itself, okay? Everybody thinks of insulin as the diabetes hormone, right? Because, you know, people think about insulin, sugar, diabetes, that all kind of thing. And that is an important and accurate story. But it does a disservice to the molecule we call insulin, because insulin as a molecule is not just a sugar regulation molecule. it also has other roles in the body. Okay, so insulin is made from the pancreas. In addition to its normal role in carbohydrate metabolism in your body, insulin as a hormone also stimulates additional bone growth by promoting the formation of additional proteins needed to grow the bones. Okay, so this hormone, in addition to its normal carbohydrate metabolism function, promotes bone growth by triggering the production of additional proteins important for bone physiology. Okay, so it's not just about sugar, folks. It's about other things. Okay, all right, and I'm going to finish right here. Then we're going to take a nice little break for ourselves. At puberty, right? At the onset of puberty, you're going to have an influx of the traditional sex hormones, estrogen, progesterone, testosterone. These are also responsible for the growth spurts that we have in our early adolescent years, where you grow from 3 feet to 6 feet 2 over a period of time, right? So the growth spurt during puberty is triggered by the sex hormones, estrogen, progesterone, and testosterone. Okay. All right, folks, so we're racing along here. Next time we meet on this topic, okay, next class, we're going to be talking about how your body manufactures vitamin D and how the manufacture of vitamin D leads to the regulation of calcium homeostasis in the bloodstream, which is then tied to the calcification of your bones. There's a very complicated pathway we need to draw out next time. That will be our talking point for at least half of next class. Okay, do you have any questions? Okay, so Amy has a question in the chat window. She's asking, when are we going over the histology packet? That's the first thing on an agenda in lab this morning, Amy. So it's coming up. Okay. All right. Okay, folks. It's about 9:19 by my watch. Let's take a 15-minute break. Let's start lab at 9:35. The Zoom channel will stay open to you. You don't need to log off. I'll see you in 15 minutes. Okay, take a little break. See you at 9:35.